sir, it's over to you.
Thank you, Dr. Avdesh, for speaking such good words for me. I do not know whether I deserve them or not, but Guru Shishya relation is like that. So I also take you as a very close to my heart, Shishya, and I always praise about your approach, about your way of things, doing things, and I take them very nicely. Thank you so much. Now, with your permission, should I start my presentation? Okay, okay.
You can say Rosla.
Is it visible, please?
Yes, sir, it is visible.
Okay, fine, fine. So,
Yes.
Control, as I said, is a key word for any engineering. Whether it is a civil engineering, electrical engineering, electronics, mechanical, computer science, whatever it is the key word. And when I say control is very, very important, then we must understand basically what is control, why control, and how control. These are the three things which go together. So I would like to have three parts of this presentation. As I named it as adaptive and intelligent control, because this is a digital age and the latest technologies are definitely the adaptive and intelligent control. Earlier I was thinking that I'll present on intelligent control only, but later on when I saw your detailed course content, then I thought I may club it with adaptive control. That's equally important. So I chose this topic as adaptive and intelligent control. So as I said, why control? What is control? How is control implemented? What is control system? Types of control system and analysis of control system. You see, I have divided these into three parts. One is the basic part of the control engineering. Second part is the adaptive control, and the third part is the intelligent control. Of course, one after another. So when I touch about the control, when I speak about the control and say what is control, any system, if you think of any system that has an inherited characteristic, it has a process, and simple process is input, process, output. This is the simplest system one can imagine. Input, process, output. When you give an input to a process, definitely by default, it will generate certain amount of output. But that output, whether it is required, whether it is meaningful, whether it is relevant, whether it is desired, that is the question. If it is not the relevant output what you want, if it is not the desired output what you want, then what to do? Then there is a word coins, that is control. You have to make certain changes in the system itself so that the output which you get should be of the desired one, or the eminent one, or the relevant one, or what you desire to have. So there comes the picture of control. Now, how is control implemented? If you want to say that in very short, you will have to go for what is a control system. Then only you will be able to implement the control process in it. And once you have a system, it is definitely a system. When you go for a control system, that is also a system. So that's why I call it a control system. So we arrive at a control system, and how this control system is operated, that is the things to know, and that is the different types of control systems are there, and then there are analysis of the control systems. And we all know that there are two types of analysis. One is the time domain analysis. The second one is the frequency domain analysis. The time domain analysis is the foremost important thing, because everything happening in this universe before you is in the time domain. But is it possible to do it always? That is the question. To my mind, it is very, very difficult. To some extent, it is very good. It is possible. But when you go for nonlinear systems, as you know, the most of the systems are nonlinear in nature, and depending on the degree of the nonlinearity, the system becomes complex and more complex and complicated. In that case, if you want to represent your control system or a system by a mathematical model, because the representation is always done either by the mathematical model or by the experimental model. So mathematical model, if you want to represent it, it becomes very difficult because that will have a lot of differential equations, difference equations and all jargon of mathematics. And to have the solution of those equations, that becomes sometimes very difficult depending on the non-linearity degree. So that's why you all know that we transfer from time domain to we convert the time domain into frequency domain by applying certain mathematical tools, like your different tools. Fourier transform, the Laplace transform is there. Nowadays you have a Z transform, the wavelet transforms, etc. etc. When you have a time frequency domain, it's a combined domain. You have some part in time domain, some part in frequency domain. Then perhaps you have to go for the Fourier transform will not work, the Laplace will not work. Then you have to go for wavelet transforms. So these are the things. These are how the control system has evolved. So I will try to share my experiences within these framework only. So control system, if I want to define, it is a system, very simple. It is a system which provides the desired response by controlling the output. That is the crux. If I want to have the output, any output I want, then I don't require any controlling system. That whatever output I'm getting, that it strictly depends on the input, and I'm happy with it. But if I want to control it, then I need to have a control system. And traffic lights control system is one of the simplest examples. You can imagine that there are lanes, different lanes. The sequence of input signal is applied to this control system, and the output is one of the three lights that will be on for some duration of time. Red will be there, or green will be there, or yellow will be there, depending on the people can decide their path and move their vehicles. Nowadays in Japan and other countries, in India also, this traffic control, earlier it was a microprocessor and a microcontroller based system. But in Chandigarh, I know they have at least in three light points, they have gone for fuzzy based system. And fuzzy based system, you know, by applying load cells, etc., they will like to have the traffic, actually traffic sense. They will sense the traffic. Many times it happens that the traffic is not much there and it is still red because it has been designed for that. It has been programmed for that. So that is not a good system. So they will sense the traffic, and depending on the traffic, the lights will be on and off. So that is what is the evolution in the field of control. Control system manages, commands, directs, or regulates the behavior of other devices or systems using control loops. Naturally, if you have a control loop, which is a feedback type of control, you may have an open loop system, but the open loop system doesn't have any control on the output. The output, whatever you get by default, the system produces certain output that if you are happy with it, it's okay. You don't require any control. But if you want to have a desired output and the behavior accordingly, you want to regulate it, then you have to have control loops, and that is in the form of feedback system or closed loop system. So it can range from a single home heating controller using a thermostat, as you have in your geysers and your heaters, other heaters, and controlling a domestic boiler for your geyser, or a large industrial control systems which are used for controlling process or machines. You can have a very big system also, but that is also controlled, and a very small system also, that is also controlled. Everything is controlled, whether it is a process or a machine. Nowadays in domestic affairs, you have washing machines. We are fuzzy based washing machines. It will sense the dirt. It will sense the load of the cloth to be washed, and accordingly it will take the detergent. Accordingly it will take the water, and accordingly the program will be done. But earlier it was only microprocessor based, and you have to program it, and the system will run only as per your program. But this is how this digital world is coming in picture, and it is framing the adaptive control, the intelligent control, etc. The fridge also has become a fuzzy based fridge, and according to the temperature, according to the material kept inside, according to the capacity of the device, the control is envisaged, and it is there. Now, types of control is, if you say, so basically there are two types of control systems. One is the open loop control system and the other is closed loop control system. This is not new to you. All of you know it. Or what is an open loop system and what is a closed loop system. An open loop system control system does not provide any opportunity for the user to make any control to the on the output, whether the closed loop control system does so. So this is the open loop system, input, control system, or you can also say the process and output. That is the simplest control system available. Input, process, output, or input, control system, output. Here there is no connection between the output and the input. Whatever the process is, whatever the control system built in is, according to its effectiveness, according to its efficiency, the output will be obtained. And you may be happy, you may not be happy, you cannot do anything out of it. And that is the simple open loop control system. Then further, people thought that will not be of much use to it. So they went for closed loop control system. And the closed loop system, as you all know, looks like this. You have a controller, you have the plant which is to be controlled. The feedback elements are there. That means you need to have a loop. I was talking about the loop, which is known as the control loop or the closed loop path, or you can say feedback elements. What is this loop is doing? This is nothing but getting some feedback from the output and referring it to the input, the set point, and error is being obtained by the error detector, differentiator, maybe differentiator, and then error signal is obtained. So that becomes the controller signal as input. So that goes to the controller as input, and the controller works on it, the error signal. Accordingly, it produces a certain output, which is the actuating signal for the plant, and the plant takes it and accordingly gets control. So this is the simplest example of closed loop control system, or a one loop, you can say control loop, or a closed loop control system. For continuously modulated control, if you want to have a continuously modulated control, means the control has to be continuous for certain time and it is to be modulated also. A feedback controller is used to automatically control a process or operation, whatever it is. It can be done for an operation also. It can be done for a process also. It can, the process could be anything. It could be bottling. It could be manufacturing. It could be a milk product process, etc., etc. Or it could be an operation also, which are normally done in the manufacturing areas. So it is a continuously modulated control, and feedback has to be there. That controller is designed. The control system compares the value of or status of the process variable, we call it PV, that being controlled with the desired value or the set point. Dr. Aldes was just now talking about the set point. The set point is one thing which is to be achieved. So I want to be ideally I want to have the set point, and that is always set. So it is known as set point. That thing is fixed. So it is known as set point. And with the process, it is varying because of many things, parameters of the system, temperature, pressure, longevity, etc., etc. There are many things, so we call it process variable. So the process variable is definitely depending on the situation, depending on the condition, depending on the environment, depending on many things. So that is changing. That is not the fixed one. So that has to be compared with the set point, which we have already said as a set point, and we say that the process variable should be as near, as close to the set point as possible. So that is what the control system is doing. This is applied the differences and the control signal to bring the process variable output of the plant to the same value as the set point. We want to put it as near as possible to the set point, and there are controllers which will give you 100% set point output from the controller. So that is a very effective and very efficient controller. This is how the difference was little, then it becomes still little, then it is very close, minutely close, and then become absolutely the set point. This is what is the achievement in the digital age of control, and we have gone for adaptive controls, intelligent controls, etc., etc., which were earlier not existing. So now comes the adaptive control, as I said. So adaptive control, what is adaptive? Adapt karna. Adaptive means if there is a change in the process variable according to the conditions, the environment, the parameters, the PV, process variables, they change. So they change, but the system has to adapt it to the set point. So adaptive control can be defined as it refers to a control method that is used by a controller that must adapt to a control system with varying or uncertain parameters. Varying means uncertain. A parameter which is uncertain because it is varying. It is not a constant parameter. It is varying. It is time varying. So naturally we have to adapt certain things that it is referred to that, but it maintains the same, and it is changing. It is taking care of the change in the process variables. Adaptive control, on the other hand, adapts to changing control parameters. It takes care of the control parameters which is changing and has the ability to control the process more effectively. It is obvious that when it is taking care of the control parameters which is changing in nature, since it is adapting that, so it automatically develops an ability in the system that control the process more effectively. So set point is earlier reached, or it is very close. It is a precise controller. So I would say adaptive control is nothing to have a very, very precise and effective control. Adaptive control is the capability. It can also be said as it is the capability of the system to modify its own operation to achieve the best possible mode of operation. Now this is very good that it can adapt. It has the capability to adapt the system in such a way that the system itself is modified to its own operation, so achieve the best possible mode of operation. अगर आपको पता है कि मुझे बाएं थोड़ा जाना है, दाएं कम जाना है, so you will adapt yourself to go inside in a path. You will opt for a path which is as near as possible, which will be the optimum path. So optimization actually was the technique which was obtained, which was taken in the adaptive control, and it gave very good results, very precise control process. Adaptive control can be described as the changing of controller parameters. Naturally, the controller parameters are being changed online based, because these days, earlier it was inbuilt in the system with the help of certain hardwares. When microprocessors were there, microcontrollers were there, even computer was there. So it was programmed in such a way that it will take care of the controller parameters. It was changing, but nowadays it's one more step ahead in the automation, and the parameters are online changing on the changes in the system operating conditions. Why the system changes, why the parameters change, it is obvious. It is very, very simple to understand, because the conditions are changing, the environmental conditions, the system conditions, they are changing. Since these conditions are changing, the parameters are changing, or the process variables are changing. So adaptive controller has to take an action in such a way that the system manages the parameters in such a way that they are very nearing the operating conditions. The adaptive controllers, based on analytical techniques, can provide excellent performance and improve the dynamic performance of the plant by allowing the parameters of the controller to adjust as the operating conditions change. Similarly, what I was saying, that it has the ability, it is capable of changing the parameters as per the conditions, change in conditions, environmental change or system changes. So say for example, temperature is changing, or pressure is changing, or stress is changing, or any elongation is changing, something like that. So when that is changing, that is a condition. So because of that, the parameter or the process variables are changing. So the adaptive controllers will definitely take care of those conditions, and accordingly it will vary. It will control the parameters, and naturally it will almost stick to the set point which was earlier fixed for the control. So proper care needs to be taken to make them robust, especially under large disturbances. Controller robustness can be improved by employing artificial intelligence, that is AI techniques. Now, with the digital age, the adaptive controller has got one more step ahead. How? It has been now using the artificial intelligence. Now one can ask if it is using artificial intelligence process, say for neural networks or fuzzy logic or NFIS, etc. It's a neurofuzzy, etc. These are the techniques which are used in artificial intelligence. So if you are using this, then how is it different than the intelligent controllers? Well, intelligent controllers are final controllers which have actually proven to be the agents for the latest controllers, and that is totally based on AI. And AI, different techniques are there. Very much techniques have been now applied. Even they have gone up to deep learning. So that is the latest technology of that is latest domain of AI. I would say subdomain of AI, which has been now given. So now we don't call it an adaptive controller, although the lines are same, the framework is same, but it has been renamed as intelligent controllers. It is possible to implement either the entire algorithm, because whenever you have a program for controlling system, you have to develop certain algorithm. So either the entire algorithm using AI techniques, or by integrating analytical and AI techniques. You have both analytical technique also, that is the mathematical technique, and you have some AI techniques also. Some part of it is based on the mathematical analytical approach, and the rest is based on the AI technique, that is artificial intelligence techniques, such that some functions are performed using analytical approach and the rest using AI techniques. So it is a mix. It is an amalgamation of the two. But in intelligent controllers, we'll say that it is not much of analytical approach is there. It is almost totally now intelligent, which is AI based. So successful implementation of purely analytical, purely AI and integrated approaches is illustrated by application to a power system stabilizer to improve damping and stability of an electric generating unit. I, being an electrical engineer, I always like to give electrical engineering examples. And here you have a generating unit, means power system generation, and you have stability is one of the important areas where electrical engineering are doing. Lot of engineers are doing lot of research, and they have found that the system stabilizers, their function has been, their performance have been improved a lot in the area of damping and stability of an electric generating unit by applying all these analytical, purely AI and integrated approaches in their research work. Well, some of the research works are very good research works have been done in IIT Kanpur and also in IIT Mumbai, and there you will find their papers are there, IEEE papers are there, wherein lot of controllers have been designed, and they are now using lot of mostly they are doing AI techniques, integrated approaches being done. If you see the model reference of an adaptive control, it looks like this. You have a reference model, the adjustment mechanism is there, and the controller is there. Of course, the plant which needs the control is there. So what you are doing is you are giving the parameters obtained from the adjustment mechanism to the controller. Also, the reference model input is given to the controller. But then there are other input given to the controller. There is one more input given to the controller. Third one that is obtained from the adjustment mechanism. As you see the plant, which is not at the plant, which is plant as well as the output of the plant, which is Y. So that is given to the controller as feedback, and the controller then finally with these inputs, that is reference model, Y reference, adjustment, this parameter, and the output from the output, the feedback from the output, they will form the three inputs for the controller, and finally the controller generates a U, which is the input for the plant, and the plant will generate finally the output, which is the controlled output of the plant, which is in the form of Y. So this is in general the model reference for adaptive control. And another thing is you may have so many identifiers. So identifier 1 to identifier M. It is dotted there. That means identifier 1, identifier 2, identifier 3, and so on up to it goes up to identifier M identifiers. So what is there? You have theta 1 from identifier 1, theta M from identifier M, and theta is this the output from the second layer. It goes from the first layer to the second layer, and second layer output in the form of theta cap, it goes to the system, and system output is also obtained from the identifier M as X. So there are three inputs again to the system. One is theta cap, one is XR, the reference input, and the other one is output X. So with these three amalgamation of three inputs, the system generates an input for the controller, which is in the form of Y, and the controller finally gives the output in the form of X. So this is another form of explaining the adaptive control. From instrumentation control engineering point of view, if you see, you have identification package, you have the process, you have the actuation, and you have the control system. So feedback loop is there, set point is given to the comparator, and the feedback is in the form of the negative. So error is generated. That goes to the control system, and from the modification stage, which is manipulated variable, and also from the output, that also goes to the identification package. And these three inputs are given to the actuation, that is the actuator, and three outputs obtained from the actuators are then given to the control system, and one error in the form of set point and feedback output error, that is also fed to the control system. Then that is given as the manipulated variable, and this manipulated variable is given to the process, and the output is obtained. So this is instrumentation and control engineering point of view. You have a block from like this of this is also sometimes known as self-tuned or adaptive control. So this is the block diagram of a self-tuned control. Self-tuning control is also important. You will have process model parameters estimation. The process is there, controller is there, and the feedback is there. So you have a control calculation. The same thing, controller has to be calculated here because the parameters estimated in this model, parameter estimation goes to the controller calculation, and it goes to the controller. So you have again there is an error which is obtained from the feedback, output feedback, and the set point. And this error and from the controller calculation, the controller settings are given to the controller. The controller will generate the output output which is taken to the process as input, and the Y output is generated. So this is another block diagram form of we call it self-tuning. That is not the kind of adaptive control. This is another same lines you can explain yourself. You have the set point, you have the inner loop, you have the outer loop. Those two loops are there. So there is one inner loop and there is one outer loop. So auxiliary measurement is there and adjustment mechanism is there. The updated controller parameters are there. Outer loop is given to the controller. Inner loop is also the set point character, that is the comparator. In the form of error, it is also given to the controller. And finally, the process sends you the control output, which goes to the plant or the. So adaptive control functions, there are three functions of adaptive control. In general, they are the identification function, which is to identify what is the change, decision function, what is the change required, what is to be done, and modification, how much change is to be done. So these are the basic functions of the adaptive functions. You can also show it like this: the identification function, the decision function, the modification function. The main idea of adaptive of the cutting process by automatic online determination of speed and or cutting. It is an example of a speed and cutting machine, lathe, etc. The AC is basically a feedback system in which cutting speed and feed automatically adapt themselves to the actual condition of the process. They have to actually adapt to the conditions, actual conditions, and are varied accordingly to the changes in the work conditions as the work progresses. Now later on, newer controls and novel control techniques started coming up. There were a lot of research. You all know that in the field of control engineering, there is a lot of research is taking place. So new control techniques are created continuously as new models of intelligent behavior are created and computational methods developed support them. That means the intelligent behaviors, intelligent algorithms were there, and that is definitely dependent on computational methods. So these are known as intelligent algorithms for supporting these type of techniques. So then this was nothing but the intelligent control. So intelligent control uses conventional control methods to solve lower level control problems, and conventional control is included in the area of the intelligent control. I mean, lower level can also be included, and also the conventional control problems can also be included in the area of intelligent control. The idea is just to have as precise and as quick control as possible to achieve precise and quick control. So efficiency is higher, preciseness higher, accuracy is higher. This is what is the intelligent control aims to achieve at. Intelligent control attempts to build upon and enhance the conventional control methodologies to solve new challenging control problems. There are a lot of new challenging problems, as you all know. In the control problems, you have mathematical problems. You have to have a lot of jargon, computation jargon to solve them, and then iteration problem could be there. Computation time could be very high. So these are the problems which are coming as challenges in the way. But this intelligent control attempts to build upon and enhance the conventional control methodologies to solve these problems. So they make it more easy. The intelligent control makes it more easy, less complicated, faster, more responsive. That is the intelligent algorithm, and that is the achievement of the intelligent control. To control complex systems, one has to deal effectively with the computational complexity issue. This is what I was trying to mention you, that there is a lot of computational complexity. Many times you write a program, you will find that you go to the infinity loop and it will not converge at all. That is because of the lot of iterations it takes, and then it gets derailed, and that is the computational complexity, and you don't reach to any solution. So that kind of things have been avoided with the help of this intelligent algorithm built in the intelligent control systems. So intelligent control deals with the application of artificial intelligence, knowledge base, expert systems, fuzzy logic, and or neural networks, or controlling complex physical processes that are difficult to control using conventional methods. Now, physical methods, as you said, that as you think that there are a lot of complexity comes in the way, and it is very difficult to obtain the solution. That way, with the help of application of artificial intelligence, knowledge base, expert systems, fuzzy logic, neural network, neurofuzzy, ANFIS, etc. Lot of work has been done in this area, and lot of intelligent controllers have been designed, and they have been derived out of the intelligent algorithms, and that way the researchers have achieved lot of removal of complexity in the area of control, then especially the computational complexity. So intelligent control is, in short, you can say it is a control, it is a class of control technique that use various artificial intelligence computing approaches like neural networks, Bayesian probability, fuzzy logic, machine learning, reinforcement learning, evolutionary computation, genetic algorithms, etc. Now, when I talk of genetic algorithms, definitely this is an optimization technique. So lot of optimization technique has also emerged in the field of intelligent control. Now PSO based controllers have come. So there are other things of ant colony invention, then bees, like that. So many optimization techniques have taken place. But since genetic algorithm is one of the best tested and most dependent optimization technique, so this is mentioned as one of the intelligent controllers. But many other optimization techniques have also come in a very large way for intelligent controllers. Intelligent control can be divided into the following major subdomains, that is neural network control, main, of course, you can say machine learning control, and reinforcement learning control. These are the three main domains of intelligent control. So Bayesian control, then fuzzy control, neurofuzzy control, expert system, and genetic control. Of course, I said genetic control is one area which is actually the optimization techniques used, and many other than genetic also have come. Optimization techniques have also evolved. So neural network control, in very short, I will like to touch them. Neural networks have been used to solve problems in almost all spheres of science and technology. So neural network, as you all know, it is the upcoming area. It has already there. It is not a new area now. It is too much of neural networks have come in the field of engineering and other fields also. So control basically involves two steps, that is the system identification and the control. And you all know that the control is has got a lot of training data and then feedback controllers, the methodology, etc., etc. So system has to be identified and then the control has to take place. So it has been shown that a feed-forward network with nonlinear, continuous and differentiable activation functions have universal approximation capability. Though this is a very vast capability, this neural feed-forward network. Of course, feed-forward, feed-backward also is there, but feed-forward is very, very important, and that is universal approximation. It has got a huge capability in solving problems. So recurrent networks have also been used for system identification. Given a set of input-output data pairs, system identification aims to form a mapping among these data pairs. So they can map the data pairs, they can have the training data, they can separate them and build upon the control, whatever control is done, which is effective and very, very responsive. Such a network is supposed to capture the dynamics of a system. For the control part, deep reinforcement learning, which is also known as deep learning, has shown its ability to control complex systems. This is the most latest reinforced and deep learning, most latest area wherein lot of capabilities have been developed. Not much of work has been done, but a lot of research has been done, and people are asking for deep learning to come in the field of control also. And I'm sure that if you see some of the latest the literature, then you will find, especially the research work going on in the IITs and NITs, you will find that deep learning is taking a lot of effective controllers. Bayesian probability has produced a number of algorithms that are in common use in many advanced control systems, serving as state space estimator of some variables that are used in the controller. This is earlier also there, and you know, we're very famous Kalman filter and particle filter. These are the two examples of popular Bayesian control components. The Bayesian approach to controller design often requires an important effort in deriving the so-called system model and measurement model. One is the system model, one is the measurement model, and measurement model minded, it is the part of the feedback. So unless you have a measurement model, you will not be able to impart any control in the system itself model. So we have to generate the system model only by taking help of the measurement model. So that has to be very effective and efficient, accurate and precise. So which are the mathematical relationship linking the state variables to the sensor measurements available in the control system. So mathematical linking has to be there with the intelligent applications. In this respect, it is very closely linked to the system theoretic approach to control design. Theoretical approach of the control, which is we say as the classical control theory, that is also that is the mathematical part, that is very important also, but that is to be properly linked with the intelligent algorithms, and then only the latest control systems can be designed. So this is in general, you can see non-linear system dynamics linearization, then comes the intelligent control system core. Then there are three. One is the fuzzy logic based modeling and control. There's a linear integer system, FOPID control they call it, and then artificial neural networks based on modeling and control is also there. Then controller structure determination using genetic algorithms. There can be other algorithms also. They all find input. They all generate input to the intelligent control system core, and finally the core, the model predictive control is generated from the intelligent control system, the core. So you can imagine that the core of the intelligent control system is so very effective, efficient, and also mathematically oriented, that it can generate the model. Predictive control. Predictive means it will understand what is the change in process variability, what is going to happen in near future, and accordingly it will adapt. So it is adaptive controller mixed with intelligent techniques, artificial intelligence techniques, which gives you the predictive model control. Intelligent system and overview, you can say the goal, the expert system, the fuzzy NN system, neurocontroller, and finally the robot, which will actually carry on the direction or the orders. So there are three levels. One is the learning level, the other one is the skill level, and the third one is the adaptive level, adaptation level. So there are three experts here: expert system, the fuzzy NN, the neuro-fuzzy controller, and finally it all will go to the robot, which will actually devise the control action on the plant, on the system. Is also same thing. You can have an example of the profit, the product, sale, market, etc. An example has been given, and that is also intelligent control. How does it work? So this is also controller interface, recommender, evaluator, monitor, and supervisor. All these things are interconnected to each other. Now it is a bi-directional thing. You cannot have one direction. The knowledge base has to go to recommender. Similarly, the recommender can approach the knowledge base. Similarly, evaluator, monitor, supervisor, controllee, and the controller input. So all are bi-directional informers, and the data passes are there, the information passes are there, and finally it is pooled in the knowledge base, and that is used for developing a predictive controller. I would say the intelligent or the predictive controller. So this is one example. You can have SCADA system, you can local PC, you have a central PC coordinator, and all the local PC and systems are there. So how you get the information, how you feed the information, how you feed back the information, and how you incorporate the control process. This is a simple block diagram. It can be continued like that. When you have a system, analog system, so A to D converter is there, that will go to the fuzzy controller, because fuzzy controller only works on the digital, and then from there again you have to convert it into analog, which will go to an execution model, which could be a valve, which could be anything where that works on analog signals only, and that will go to the control object, and of course there is a feedback which goes to the sensor, and it is corrected there in designing in finding out the error. So intelligent control system and overview, it is also infrastructure market, social information, expert system, modeling based decision, situation analysis based decision, information about current situation, agile manufacturer system, etc. And then the DM decision is there, the person is there on the laptop, on the computer, and it feeds accordingly the informations to the coordinates and decision making system, and that generates the controller signals. This is in general, you have controller, you have plant, the disturbances are also there, the sensor output through sensors are measured values, and the error is generated as an old system, what we used to do earlier also. So this is what is control system. It has a control algorithm, the actuators are there, the dynamical system is there, and the sensors are there. These are the basic 3-4 basic things, and from the control algorithm you will generate the signals so that the control is devised. Whole control system is devised with its signals and commands. This is some smart intelligence GSM controller, an example. You have automation application, you use this. Then you have a tractor example. Automatic tractor, main control center of tractor is there, sensor module is there, GPS module is there, speed control module is there, self-positioning recognition module is there, then path recognition is there, communication module is there, automatic obstacle avoidance module is there, information data transmission module is there, and image information data receiving. So many things when given to the main control center of the tractor, so it almost becomes an automatic control of the tractor, and that is what the crux of intelligent control. Quality management can also be done by machine learning systems. You have AI framework, modeling data, you have operational data, that this part is operation, this part is development. So architecture, detailed design, requirements, non-AI components, application of AI plus non-AI components, and these all are integrated to each other. So quality management can also be done. This is what is machine learning system, and that is a part of your intelligence system. So machine learning, what, why, and how. I mean, how it is done, different blocks are there, why it should be done, and how it is done. So these are the areas. Similarly, AI versus machine learning versus deep learning. And then applications of intelligent controllers. Some of the major applications of intelligent controllers are power system plant control, chemical plants control, fertilizer plants controls, pharmaceutical plants control, steel plants control, manufacturing plants control, heavy machines industries, automobile industries, power electronics controls, medical electronics control, fax controllers, custom power controllers, and robotics. So these are some of the latest applications of your intelligent application, along with adaptive, semi-intelligent, that is adaptive and intelligent controllers. That's why I've merged them together, and these are some of the applications, major applications in this area. So conclusion, if I say, then in nutshell, it can be said that intelligent control system combines the mathematical theory of control with the various AI techniques. That is, the mathematical theory cannot be avoided. You cannot say that the classical control theory is just you throw it away. No, you have to have those mathematical theory, and that is to be amalgamated with the AI techniques to make it more precise, to make it more efficient, to make it more responsive and accurate. So I conclude with the remarks that the intelligent control system is the latest control system, which is an integration of the mathematical theory of control and the AI techniques. These words, I would like to conclude it here, stop here, and I would like to thank the audience. And now you have any questions you may ask, please. Hello. Hello.
Yes, audience, please.
Any
Anyone,
questions?
they can unmute and ask the question directly.
Hello.
Yes, we are able to hear you. Yes.
Yes, sir. Sir, I am Susukun Roy. Sir, I have one question.
Yes, please.
Yes, sir. Sir, in your slide, you have told the facts controller that have used in the intelligent control techniques. So, can you explain these things? I mean, what are the broad areas that?
Yeah, fax controllers are now being used, especially in the area of custom power. Custom power also are fax controllers. They have not been used, but the research, I said the research is, lot of research is there, and in very fast future, you will find the applications also. So I would say it is under research, and lot of work has been done, especially in the area of fax controllers and custom power applications, wherein they are, because earlier it was all adaptive controllers, AI techniques were used, so it was semi-automatic techniques, or you can say semi-intelligent techniques. But nowadays deep learning is also being used, which is definitely a part of intelligent controller. So that is under research, and very soon you will hear the application, actual application.
Okay. Thank you.
Hello. Yes, please.
आठवलं चेंज करून बायोडाटा.
Hello.
ठीक.
Sorry.
Yes, please. We are not able to hear you.
Any questions, please?
Good afternoon.
Yes, please.
किसको बुला रहे हैं? फैकल्टी को?
No. You are not audible properly. Varsha? Audience, please. If anyone having any questions. Even you can write in the WhatsApp group. I can just put that question on behalf of you.
Yes, yes. Hello.
Yes,
Yes,
please.
कोणते एक्झाम्स? बरोबर. बोल ना. पिवळं. बरं, पांढरं. हां. बरं 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 बरं. हो, ठीक आहे.
I believe now there is no further questions from the audience. So thank you, sir. Thank you for delivering such a very nice lecture.
Thank you.
Thank you.